Average Nucleotide Identity Score, or ANI score, is basically a value that can be calculated in genomics to assess the similarity between the nucleotide sequences of two genomes. In this video, I would like to prepare a simple pythonic function to calculate this value, and later on I will also build some amount of multiprocessing functionality into it so that we can see the limitations as well as the advantages of using multiprocessing in generally bioinformatic tasks. Um, so to begin, ANI values are basically calculated by aligning the sequences from one genome to the other and then computing the average identity of the aligned segments. What I mean by this, I will show in a small workflow that I've prepared. Uh, Essentially, ANI is calculated by fragmenting the genomes into smaller pieces and then aligning these fragments to the other genome. Uh, After this is done, we can determine the average percentage of the nucleotide identity across these aligned regions. Afterwards, which is the last stage, we prepare a threshold. Generally, if we receive an ANI score of 95 to 96% or more than that, then we generally assume that those species are highly identical to each other. One thing to keep in mind over here is that ANI score alone cannot determine the complete similarity of the sequences. We generally also look at the genomic coverage and how much of the fractions exist, basically how many of those ANI scores were used to compute the average of the value. So an example of the usage of this kind of a technology would be delineate the taxonomy clusters between unknown FASTA sequences, where you don't know what the FASTA references origins are, but you would like to know if those are somehow linked to each other, if they are in any way similar to each other. Um, Similarly, the ANI scoring sequences, where we have very identical values, belong to the same cluster, might even indicate that they are from the same taxonomy. Here is a small workflow where basically we have 6 steps of understanding how the ANI score is calculated. We start with two genome references. The second step, of course, is fragmenting the genomes. Um, Once those fragments have been prepared, we align the fragments of the first genome onto the other and also the fragments of the second genome into the first. This is also known as the best bidirectional hits, or essentially the best reciprocal hits, so that we are not just using the first reference as a query, but also looking at the second reference as a query. This is important in case your sequences are not of the same length. So it will remove any kind of bias regarding the sequence length. The fourth step is to calculate the identity. This is essentially the identity percentage for each of the aligned pairs. This can be calculated by a simple scoring algorithm. I will be showing a very simple base by base calculation algorithm in a few minutes. Um, and this does not have to be a very complicated function. It is just to calculate the score essentially. Then the fifth step is to filter the alignments that are passing a certain threshold. So if we have, for example, a threshold of 95, then we will only accept the aligned pairs that were more than 95. And from those thresholded pairs, uh, they can also be, by the way, thresholded on the basis of the coverage. If the coverage is not a very high number, then we can also remove those alignments. And the final step, basically, after we have processed and filtered the alignments, is to compute the average of those scores. So this is essentially the average nucleotide identity score. I have prepared some FASTA files that contain very simple 4 nucleotide base sequences. My goal is to prepare a function that takes the first FASTA file as a reference and then match it across every other FASTA file in my database. The goal, of course, of that would be to generate a list of the ANI scores. We can imagine these individual FASTA files as fragments of a much bigger genome. Basically, I'm working on some kind of an extension after step three, where the alignments are already ready. Because the first four steps are a bit difficult to do if you work with very large sequences. I'm currently only working with the smaller fragment level calculation. So since this function is fairly small, using multiprocessing will not have a real impact on our overall result processing. So typically the steps 2, 4 and 5 could be performed by a simple custom script using BioPython package in Python, of course, while step 3 requires some strong alignment algorithm like seed and extend used in BLAST, or MUMMR or LAST, which are basically tools for large scale sequence comparisons. If we assume in our ANI calculation that steps 2, 3, 4, 5 take around 2 seconds, then we can test what is the impact of processing longer and longer functions. after these results, we can establish that a small scale function can be improved with multiprocessing if we are working with either a very large amount of data or processing very complex mathematical metrics or creating a big enough function that it is time consuming per iteration. So this kind of comparison also helps us understand what kind of order of the results are returned from the multiprocessing algorithm internally and how it sorts the results while it sends it back. Since my current test case was quite small, it does not really change the order of the results, which is good, of course. Maybe it would also be a good idea to explain a little bit how these mapping functions differ from each other. So IMAP and IMAP unordered, the key difference is the order in which they return the results, where the IMAP would return the exact order of the results in which you had input the FASTA files, while the IMAP unordered would return them whenever they get completed. So if the second item gets completed before the first one, then it does not matter what your input order was, the second item will still be output first. The difference between map and map async functions is that the map function will block all the results until all the results are ready, and then it will send back the output. But the map async function will keep outputting the results as soon as like a result is ready. The difference between IMAP and map is that IMAP returns a kind of bigger object. Basically, it's an iterator, and you can move over the iterator to see those results, while map basically returns a list of the results directly. Both have their advantages and disadvantages. If we are working with, for example, a bigger class of data, we would like to have IMAP in our results so that we can iterate it as an object. It is much better for data usage. The map async function, as I said before, it handles the results asynchronously, so it basically has some advantage. If you don't want the entire result pool to be ready before you see the results, you want to start seeing the results as and when they get ready, you can use this function. All right, so this is it for this video. I would also be creating a small test case in my next video so that it's all basically part of good coding practices. Whenever you prepare a small function, it's good to prepare a test case with properly doc typed and doc stringed code, so that when you refer to your code in the future, it will be easy for others to add on to it or read from it, or even for you to improve on it. All right. Thank you.